Okay, let's get started. Welcome everyone to the first talk in 2022 at the CS Colloquium. Our speaker today is Professor Roger Zimmermann. He's a professor of computer science in the School of Computing at the National University of Singapore. He's a key investigator in GRAB-NUS AI Lab, which is a joint research lab between NUS Institute of Data Science and GRAB Taxi Holdings. Before he moved to NUS, he held the position of Research Area Director with the Integrated Media Systems Center at University of Southern California, from where he also received his master's and PhD degrees. Among his research interests are streaming media architectures, multimedia networking, distributed systems, and applications of machine learning and deep learning. As you know, CS Colloquium, we invite speakers to celebrate recent promotions and awards. In this context, Professor Zimmermann attended full professorship here last year. So in that regard, we are very happy and use this as a proxy to celebrate his full promotion. With that, I'll hand off to Professor Zimmermann for the talk today.
Thank you so much, Kuldeep. It's a pleasure to give this talk. Yes, so I've been with NUS for almost 15 years now, pretty much exactly 15 years. I started in January 2007, and time has gone pretty quickly. So it's been very interesting. And yes, as Kuldeep mentioned, I do work in several areas, or I would like to say actually my research fellows and students do work in many different areas. The two big areas are basically streaming media, and the second one is spatial temporal data management in the broadest sense. So today's talk is going to be about the first area, which is streaming media. So I would like to tell you a little bit about what's going on in that area in terms of recent kind of developments and recent activities. So there's going to be kind of like three parts. So the title actually only reflects two parts, but I'm going to talk about sort of three parts. One of them is low latency live streaming, which has become very popular recently. That's like game streaming is one of those applications in that area. Then 360 video streaming, we did some work several years ago, but now I think with Facebook putting so much emphasis on metaverses, etc., so that may actually become kind of more popular again. And then the last one is something that is quite of interest to industry, which is Common Media Client Data, CMCD. So I'm going to give you some overview what that kind of standard is and what it does in the streaming world. So I would also like to give credit to all the people that I work with. So let me go back to one slide here. So Abdelhak Bentaleb was my student and has been my research fellow for a couple of years. So he has been very instrumental in much of this work. Maylim is one of my PhD students, and Ali Begin and Mehmet are collaborators from Turkey. Mehmet is a student and Ali Begin is a faculty at Özyeğin University. So you may wonder, so why should we learn, or why should we be considered about video streaming? Okay, so well, it turns out that video streaming is really a very important application on the internet. Okay, so if you look at the slide, let me get maybe get a laser pointer here. Yeah. So if you look at the statistics, even in 2016, video streaming was already 2/3 of the traffic of the global internet. Okay, and of course, all of the traffic has been increasing tremendously on the internet, but it should be nowadays. It should be somewhere between 75 and 80%. Okay, and some of the big media streaming companies like YouTube and Netflix, they account for a significant fraction of the total internet traffic. And you can see here that Netflix, I think this is during peak hours in the evening, they account for about 1/3 of the whole internet traffic. Okay. One interesting part here is that video streaming over the internet is actually a relatively new phenomenon. When I started to do research in this area, most of the video was distributed over cable networks, over proprietary networks, which of course still exist. But this phenomenon of actually delivering video over the internet is called over-the-top streaming, OTT, and that is relatively recent. And because the internet was never designed to carry video traffic, there's quite a lot of work has been going on to make it actually work and make it work well. Okay. So as kind of an illustration of how important video streaming is in terms of the internet, you may remember this character from the Game of Thrones, right? So this is Gregor the Mountain. Okay, he's played by this Icelandic professional strongman and actor. It's difficult for me to pronounce his name. I don't know exactly how. It's something like Hafþór Julius Björnsson. So that's him and his wife there. Okay, so you can consider this. So he is the video streaming part of the internet, and she is everything else. Okay, so that's about the size relation in terms of the traffic. Okay. So as I mentioned, it used to be that we had all these proprietary networks, cable networks, Comcast and Charter in the US, but much of this has now moved to the internet and to IP-based networks, right? And in pretty much every country, and even the traditional cable networks such as Comcast now have basically moved their platform onto IP networks. Okay, so one effect is basically that there's a tremendous amount of what we call video on demand. Right? Video on demand streaming is, movies, sitcoms. When the content has been pre-recorded some time back, it's now stored on the server, and the latency is not really all that important. So you want a quick startup time, but the end-to-end latency is really not important in that sense. Okay, so here is a breakdown of kind of a new category, right? So what happened more recently, the last sort of 5 years, is that people became interested in live streaming. So, for example, you do streaming of games, right? And so there's the company Twitch that pretty much that's all they do, basically. People stream live over the internet. You can have auctions and e-commerce services. You could have live events, live sports events, etc. So in that case, one of the very important parts is the end-to-end latency, which we also call the sort of the glass-to-glass latency. And glass-to-glass refers to the glass of the camera to the glass of your display, right? That latency needs to be short when you have a live event, because people may be using other devices. They may be using WeChat, they may be using WhatsApp, social media, and if the video is way behind the actual live event, then your friend may text you that, oh, there was a goal, but you don't see it on TV. You're still waiting for the goal to happen. So that is not a good situation. So, but you can see here in these statistics that basically in 2016, the live video part was a tiny fraction here. And then in 2021, it has grown to quite a sizable chunk now. So let's have a quick look at some of the background of video streaming. So in the early days, even of IP streaming, the protocols that were used and that were standardized were called RTP, RTSP, and RTCP, which is basically a kind of a triplet of protocols that work together. And they were based, RTP is based on UDP packets. Okay, so basically the RTP transports the actual media data, and it does it in very fine-grained with UDP-sized packets, maximum 1500 bytes. So what happened there is that the server became very complex because you have to send small pieces of data very precisely. So you have a lot of scheduling overhead, and it's a complex server. It could be using either TCP or UDP, and it was difficult to cache, and the standards were never truly standards in a sense that every company that used these protocols made some proprietary additions. So the clients and servers were never fully interoperable. Okay, but one big benefit was that the end-to-end delay was short, so 100 to maybe 500 milliseconds. And this is still used today in something called WebRTC. So WebRTC is a protocol that is built into your browser. All the major browsers, they support this. And the idea was basically to have this, put some of this library code into the browser so that you can relatively quickly build up a video conferencing application. And so nowadays with a little bit of JavaScript code and the browsers, you can actually have build kind of like a Zoom application. Of course, for a real Zoom takes a little bit more work, but it's relatively easy to build a sort of a two-way teleconferencing application. However, that's not where the big traffic is. The big traffic is where we have do video on demand. And this has pretty much been taken over by what we call DASH, Dynamic Adaptive Streaming over HTTP. Okay, and so DASH uses HTTP as the underlying protocol, and it uses HTTP GET commands to get larger segments from the server. Okay, so rather than getting small 1500 byte packets, we're getting larger segments that are between 2 to 10 seconds long. Okay, this has several benefits, and one of them is that you can use a regular HTTP server. So there's no, you don't need to build a complex streaming server, and also that because it's HTTP, it uses port 80 and it goes very easily through firewalls, etc. Now, one of the main objectives of streaming on the internet is to achieve decent quality of experience. Okay, and that's where the adaptive part comes in, because we all hate it when video stalls, right? When we get the spinning wheel that says, okay, need to wait for data to buffer. So how do we use the internet, which was never designed for video, and put some clever protocols on top so that we can get good video quality? So with Dash, as I mentioned, it has a number of advantages, but the disadvantage is because the segments are relatively long, the 2 to 10 seconds, you will never be able to achieve very short latency. If your segment is 10 seconds long, that means the segments need to be produced at the camera side, at the recording side, and it will take at least 10 seconds to capture the data until you can send it to the receiver. So your latency is going to be at least 10 seconds. Okay. So Dash is not useful for two-way applications such as video conferencing. Okay, there's a question here. Okay, so there's basically three different types of streaming applications. One of them is video on demand, where we generally don't really worry about the end-to-end latency because the content is not live, right? So if you watch a sitcom or Friends or something like that, it doesn't really matter. I mean, the data needs to arrive at a reasonable time, but there's no specific latency required. Then there is another application, which is live streaming one way. Okay, if you do live streaming to a large audience, like a gamer, then you want to have relatively short latency, but it doesn't have to be so short as in video conferencing. So video conferencing is kind of the third application that's two-way live streaming. Okay, and in order to do two-way live streaming, you have to have very short latency, less than half a second, because otherwise the interaction becomes very awkward. Okay, so when we talk about low latency dash streaming, we talk about the middle application where we want to stream in one direction and we want to have a short latency, but because there's no two-way, it can be a little bit longer than what video conferencing requires. So yeah, so that's the recent work that we have been working on is basically how do we take Dash, which is extremely scalable. So Dash has the benefit of that, you know, with a web server, you can serve thousands, tens of thousands, hundreds of thousands of users with a relatively straightforward setup. Okay, if you want to do this as live streaming one way, can we leverage Dash to make that happen? Okay. But then we want to, instead of having 30 seconds latency, you want to have 3 seconds latency, 2 seconds latency, or push it even lower. How do we make that happen? Okay. So how does Dash work? And how is it adaptive? So basically we have the, on the server side, we have the HTTP server, okay? And we have the content, and the content is going to be encoded in multiple qualities. And I have another slide that shows this in a little bit more detail. So we have the content preparation here. The content is described by what we call an MPD, Media Presentation Description. This is basically just a file, kind of an XML file that just says, okay, I have Squid Games is on the server and it comes in 4 different qualities and the length is such and such, etc. So it has this description, and then we have the client here, which the first step is to fetch this MPD from the server, figuring out what content is available, and then grabbing the content from the server. Okay. So in this MPD, we also call it a playlist, basically. So it's a file that lists all the different movies and all the qualities that the movies are available. Okay, and there is a standard for Dash, which is an ISO IEC standard and an MPEG standard as well. So if you're interested in the details, you can look that up. So how does it work in a little bit more detail? So here we have the content preparation on the left-hand side. So you can see we have the time in this direction. So we have a movie that has a certain length, okay? And then we have actually, in this case, we have 3 different encodings of the same movie. So we have the best quality, which requires bigger size, and then we have a medium quality, which requires a smaller size, and the low quality, which requires the lowest size. And then these files are sliced basically into segments let's say every 5 seconds. Okay. So now we have this kind of 2D array of these different pieces that are on the server. And then if you look at the network may have different bandwidth available. Sometimes there may be only little bandwidth available. Sometimes there's a lot of bandwidth available. And so the client actually will measure the bandwidth, and it will then fetch the corresponding pieces from the server. So if only a little bandwidth is available, it will fetch a low quality piece on the second low quality, and then here a medium quality, and then a high quality, and medium quality. And then these pieces are stitched together on the player seamlessly. So you don't notice that these are different pieces. Okay, this is a smooth playback. The only difference that you may notice is that the quality may change. And I'm sure you have all seen that. Sometimes you can see it's HD quality, it's very crisp. And then if the network becomes congested, suddenly you get some blocking and it's not so sharp anymore. And that's basically when the client has fetched a lower quality piece and is decoding this. Okay. So the way this works is that the adaptation logic is on the client side. So the client here measures the bandwidth, keeps track of the network, and then has a logic that decides, okay, what is the next, how much data do I have in my buffer? What is the network status? What is the next piece that I should fetch? What quality should I get? Okay, and this is called the ABR, adaptive bitrate logic, basically, and this is not standardized. And that's where a lot of research goes, right? So how do you come up with the best algorithm which can basically adapt the best in a changing network so that the buffer doesn't run out and the buffer doesn't overflow, okay? So that you get the best possible viewer experience at the client. Yeah, so that's a good question. Can the client really actually measure the quality of the network? So that's one of the difficult parts, right? So the client is kind of seeing as the data arrives. The client doesn't have an oracle into the network to see exactly what's going on. He can only see how the last data piece arrived and then make an educated guess of what it might do for the next piece. And that's really, that's where a lot of the research goes, right? How do you make a good educated guess? How do you have a good measuring algorithm to figure out what's happening in the network without knowing really what's going on? And the other challenging part is that there may be another 1,000 clients and they all also try to measure the network and they all also try to guess what to do next. And they may actually interfere with each other because they don't talk to each other, okay? So the way Dash works is that all the clients are basically independent. And that's when we get to the third piece of the talk, I will tell you, where industry has thought, well, maybe it might be good that the server knows more what's happening, right? Because it knows how many clients there are. Maybe it's good to actually send some information between the clients and the servers and the servers and the clients in order to get the best experience for everybody, not just for, individual clients. Okay, but because Dash works with HTTP and because it works well with firewalls, etc., it has become the dominant protocol for video streaming. So all the big players use it. YouTube, Netflix, Facebook, Amazon, everybody's using Dash nowadays. but they're all using possibly different adaptation algorithms, okay? And in order for the industry kind of to move forward, what they have done is they have set up this Dash Industry Forum. So there's a website that you can look up, Dash-IF, where all these different companies, they collaborate in a sense that because they have common interest in making a good experience for the end user, right? And so as part of that Dash-IF forum, there is a sort of reference client that people are contributing. So there's a JavaScript media player that different companies are contributing and where new technologies are tried out. And we are one of the groups that are contributing to the Dash.js player. Okay. So, but now let me actually really get into the first piece. And this is, okay. Now we want to do low latency streaming, but we want to do Dash. Okay. So here's kind of a difference between, well, I talked about the difference between video on demand and live also. But then if you go into just only the live streaming adaptation logics, there's again two categories, right? So you could do sort of more the traditional ones, which are heuristic based. So you could have some rules that say, okay, if the buffer is low and the network is congested, then I want to get a small piece, okay, because I don't want to run out of data. If the buffer is mediumly full, the network is plentiful, I want to get a large piece, a high quality. You know, kind of simple rules like that. Okay, that's kind of one strategy. Of course, nowadays, even the heuristic-based algorithms are not really simple anymore. They're based on model predictive code, MPC, and other, you know, other types of algorithms. And then you have the second type, which is learning-based. Nowadays, of course, everywhere we have machine learning, right? So why not use machine learning as well for this to kind of learn what happens in the network and how to react. And so there's been a number of recent developments. One fairly famous one is called Pensieve. And then there's this algorithm called L2A. Okay, and then there's our own algorithms called LOL, low-on-latency, basically, and LOL plus. So these are based on various machine learning techniques. Okay. So how did this come about? Well, I mean, we were already working on low latency, but then the company Twitch, actually, they put up a challenge that was co-located with the ACM Multimedia Systems Conference in 2020. And they basically said, okay, we are in this business of doing low latency streaming. Can you guys come up with a better algorithm that, you know, is lower latency, does less rebuffering, has higher quality, all of the above. And the tricky part with this type of optimization is that you have the targets that are conflicting, right? So if you want to have low stall probability, it's relatively easy to do if you just keep the quality of the video low. Then if the quality of the video is low, then the size is small, and then it's easier to transmit the pieces. But on the other side, you also want to have high quality. You don't just want, you know, less stalls and low quality. You want less stalls and high quality. So how do you optimize these conflicting goals? Okay. So our entry into this competition was the LOL algorithm, and then this was a relatively short amount of time that we had to submit. But then later we found some further improvements that we could do, and that was called LOL Plus and was then published in a journal and transactions on multimedia. Okay. So yeah, so the challenge requirements were basically, yeah, we want all of the above, you know, which is keep the latency at, this was very ambitious, you know, at around 1 second. So nobody actually achieved 1 second latency, but that was a good target to have. High visual quality, low rebuffering, and low number of bitrate switches. Okay, low number of quality switches, which can be a bit annoying to people as well. Okay, so our approach was, so we're going to use Dash. Okay, we're going to use something that is called chunked transfer encoding, and of course we're going to have adaptive playback. And as one of the tricks in the toolbox, we used a playback speed control module. And let me tell you a little bit more about that. So here we can see the different parts of the, this is mostly actually the ABR logic, the adaptive bitrate selection, right? So as we discussed before, so we want to have some kind of a measurement of the network, throughput measurement, right? We want to have some kind of a module that evaluates the ongoing quality. So try to estimate what the user kind of sees right now. Then we had this playback speed control, because one trick you can do is when you have the client buffer and you're starting to run out of data, right? And you see your buffer is going to go empty. You can actually slow down the playback a little bit. Okay, so instead of 30 frames per second, maybe you go down to 28 frames per second or to 25 frames per second, which means you're consuming less data and you're less likely to run out of data in the buffer. So of course you want to use this very sparingly, right? You don't want to speed things up too much or slow it down too much. So this is kind of a sensitive logic that you need here. And then originally we had actually two different selection that we could have, a heuristic-based algorithm and a learning-based algorithm. And then the quality evaluation was based on different factors, you know, maximize the bit rate, make sure we don't run out of buffer, make sure we don't rebuffer or rebuffer as little as possible, and let's make sure we have the lowest latency possible. So here you see the QCE model which basically encodes these requirements that I just mentioned. So there are different weights, you know, alpha, beta, gamma, delta. These are the different weights that you put onto the different factors. So for a higher bit rate, we get kind of a reward. If you rebuffer, we get a penalty. If you have a high latency, we get a penalty. The playback speed should be as close to 1 as possible, and the bitrate variation should be as little as possible. Okay. So we had these two algorithms, and here, yeah, so this is kind of an overview of the heuristic-based algorithm, which is basically, it kind of pre-computes all possible solutions, right? So in this case, we only had 3 different qualities, 200 kilobits per second, 600 kilobits per second, and 1000 kilobits per second. And we were trying to predict the bandwidth for the next 5 segment periods. Okay, so we have 5 segment periods. For each period, we need to decide, is it going to be 200, 600, or 1000 kilobits per second, which turns out to be 3 to the power of 5, 243 different combinations. So then we kind of pre-computed the quality, the QCE reward function, and the model would just pick, you know, at any given point in time, it would pick the most appropriate solution, basically, the one that it would expect that would give the best result. Okay. But it turns out these heuristic-based methods are less effective than learning-based methods, right? So our learning-based methods was based on self-organizing maps. Okay, so here basically you have this a number of different neurons, and each neuron represents a state, which represents a certain throughput, a certain latency, a certain buffer occupancy, and a certain QoE. Okay, and then you're basically sort of in one state, and you're moving to another state, and you're trying to find, you know, the most optimal state that you can get to, and then you update the model with the actual measurements that you do during the last period. Okay, so it's a relatively simple machine learning model because we have to be real time, right? So we only have maybe a second or 2 seconds or maybe 3 seconds to actually do the reaction, to do the measurements, and to do the selection. So this has to be quick. Okay. So there's various trade-offs that we had to do. For example, okay, so how do we select the weights for the different QE factors? Okay. Originally, we did this manually, but for LOL Plus we had an automatic method for this. And then also we realized that there should be more weight of rebuffering events rather than the other factors. So that was changed as well. And then, yeah, decoupling the QE features from the learning-based algorithm. So here's kind of a block diagram of the whole LOL Plus design. So we have the throughput measurement, which I will tell you in the next slide is actually, there was a good question there from Roland about how to do this, because this is non-trivial actually. Then we have the weight selection for the self-organizing map. We have the QoE evaluation that is run every time period. We have the playback speed control module. We feed this stuff into the SOM model, and we have these different factors, and we try to optimize all of this for a good outcome. Okay. Now, why is the throughput measurement difficult? Well, I mentioned very briefly earlier that we use something called CTE, chunked transfer encoding. Okay, so normally when you do HTTP transfers, you do a transfer of a whole segment or a whole block of data. Now with CTE, you can actually break that into smaller parts. Okay, which is good. This can help you to reduce the latency. You can send smaller, what is called chunks. Okay, but the problem is that the standard HTTP protocol, the server will send the chunks, but the receiver will only know the end times of the chunk. So the E's here, the E1, E2, E3, E4. This is the data that you get on the client side, the time information. You do normally not get the start time of when the chunk actually was sent. If you do not have the start information, then you can't really know how much sort of idle time there was in between, which means that if you just take the previous end as the start time of the next block, your measurement is going to be pretty wrong. Okay, so Abdelhak came up with a very clever technique here, where you actually look into the buffer. We find the start. There's a start marker here for the chunk. So we find the marker in the data, and which means we can get the start of the actual data, the timing, and then we can end minus beginning divided by the size, we can get the bandwidth more accurately. So that's one of the ways that makes our algorithm work well. Okay, weight selection, yeah, let me kind of skip over this. That's just more details there. The playback speed control also, basically the way it works is that we don't want to vary too much. We allow from going from 70% to 130%, which is already quite a lot. But then this has also, it's kind of has some rules. So if the buffer is low, for example, then and the live latency is pretty okay, then we made the playback speed maybe just we leave it at 1. Okay, if the buffer is relatively low, but the live latency is below our target, the target here was 1.5 seconds. Okay, if the live latency is below the target, then we may actually slow down speed, okay, to catch up to the target speed. And if the target latency is too high right now, then we will speed up the playback. So in order to meet the target latency. Okay. Here is the algorithm. Okay. Then there were basically 3 submissions to the challenge. Ours, the LOL, then there was this L2A, there was something called Stallion, and dynamic is the default algorithm that's in the dash.gs player. Okay. So here are some results. Okay. And you can see the green shaded part here is basically the good area. So you want to be in the good parts, right, in the improvement. And you can see that we were, compared to the other techniques, our blue bars here, we were doing pretty okay, or as well as the others in the rebuffering duration and the average latency, but we didn't do so well in the average bitrate. So our client had a slightly lower average bitrate than the other ones. Okay, so that's when we went from LOL to LOL plus, and so here is a table where you can see all the green parts is basically where we improve over the other algorithms. Okay, so, and there's a comparison for LOL plus versus LOL as well. Okay, so we were able to pretty much improve almost everything, except there's a little bit, we are a little bit behind here in the bitrate versus L2A, and in the average latency of 1.6% versus dynamic. Okay, but overall, again, this is basically an optimization and a trade-off, right? So if you look at the overall trade-off, I think our algorithm is doing pretty well. And so it's now actually part of the dash.gs code. So if you download the dash.gs code, you can run it in the browser, you can use it as a video player, and you can select different algorithms, because it's kind of like it's a test environment in some sense. So they allow you to try different algorithms, and one of the algorithms is ours. So this is the first part, LOL plus low latency live streaming. Are there any questions about this? Because then I'm going to go to the second part. Okay, I know it's quite a lot of information here, so you can maybe we can have some discussion at the end. Okay, let's quickly go through some 360 video streaming. So that's an interesting area as well. In recent years, there have been an increasing number of 360-degree cameras have arrived in the market. Oh, okay. So Roland has a question. How do they choose the setup and the network conditions? So yeah, so Twitch basically had a test bed that they set up, and they had specific network profiles that they were testing, actually quite harsh, sort of artificial profiles, stair steps and things like that. But they basically gave us the different network profiles, and they were testing all the different algorithms with those profiles. Another choice, of course, is to do network traces, right? To get traces from real streaming sessions and do tests like that. So we do that also when we publish papers. But the good thing about these synthetic profiles is that everybody can reproduce them for different papers at different times. Okay, so 360 video cameras, they have become much cheaper in recent years. So you can now, buy them for less than $300, $200. So we have done some experiments with the Samsung Gear camera. Now, one of the interesting parts about 360 streaming is that, so you have 360 degrees, right? And you think that, okay, that there's a lot of, let me see, this is a high resolution, right? This is 4K. But 4K, if you distribute 4K over 360 degree, it's actually not a very high resolution, right? If a regular camera has maybe 120 degree view, which is only a third of this, so it's a third of 4K, which is not terribly much, okay? So in order to have high quality 360 streaming, you really need very, very high resolution video, okay? So one of the fundamental problems with 360 degree video is that you record a sphere, and then you need to somehow represent the video of that sphere in a file. Okay, so how are you going to represent that? So there are different layouts, basically, how to put the video into. Usually, you need something that's kind of planar in order to work with it. And I'm going to show you. So there's basically this equirectangular, which you know from regular maps, right? When you take the world globe and you want to put it on a map, you use an equirectangular projection, okay? Then there's this other thing called the cube map, and which basically projects the sphere onto a cube in the middle, okay? And then it looks like this. So let me show you the equirectangular projection here. See if this okay, this doesn't run. Oh, okay. Now it's okay. You can see that. So this is equirectangular projection. You can see all the distortions basically. Here, the horizon is a bubble. Basically, the straight cables are not straight at all. So you get a tremendous amount of distortion. This is the megazip in Sentosa, basically. This is a recording that we did my student and postdoc at the time, Yifang, she did some recording, and you can see there's lots of issues with stabilization, distortion, all kinds of things. So the question is, how do you actually watch this, right? So watching it like this is really not very pleasant. So one way is to have a narrow field of view, just to cut out a certain piece, and then let the user kind of pan and up and down, and sort of just move around and look around, right? But this can be kind of tedious as well. So so in terms of representation, we have the equirectangular projection, then there is the cube map projection, which makes better use of the amount of data. If you look at the equirectangular, basically the poles here, this should be 1 point, right? The poles should be represented as 1 point, but they are represented as tremendously long lines. So the data is sort of stretched out and it's fairly wasteful. Okay. So the cube map projection is better. So how would you fit this with an ABR scheme? So here is a possibility, right? So we have different qualities. We have different cube maps and different qualities. But then you want to further optimize it to basically where is the user actually looking. You want to have high quality where the user is looking. So for example, if the user is looking to this part of the cube or the sphere, that should be higher quality than the other parts. So you have all these different representations. You can have multiple different qualities for each one of the tiles, which you end up with n times k number of tiles on the server, and then you need to stream them at the right time to the client to make sure that it appears seamless in the headset. So that's definitely a very interesting application. And so here is the tile-based approach, where you have sort of a viewport. The viewport is what the user is looking at, either with a headset or by projecting it onto the screen. And this should be high quality, right? And everything else can kind of be lower quality around it. So how do you do the tiling, and how do you fetch the tiles just in time to give an optimal performance? Okay. One of the drawbacks is that you may end up with thousands, tens of thousands of files actually on the server because of all these different tiles and all these different qualities. So it can be kind of a messy affair. Okay. One interesting aspect of 360 video is that it doesn't really have sort of a viewing direction, but many times when the camera is moving, there is sort of an implicit moving direction, right? So you're actually, the camera, So many times you get sort of this implicit moving direction because the person was walking with the camera or driving in a car, but the camera may have faced in, maybe have been rotated in some ways. Okay. One way to compute the moving direction is using structure for motion, which is normally used to reconstruct sort of 3D buildings from multiple views, okay? But as a side effect, you can also get kind of the camera motion as well. So in this case here, let's see. So in this case here, this is just 3 different images taken at 3 different positions. This is the front of a church, and you can see you get these kind of like voxels in space, okay? And then you can kind of warp the images onto these voxels, and it gives you kind of a 3D view with, of course, some distortion because there is no there's not enough detail there to do a perfect representation. Okay, so we did this with our video from Sentosa as well, but in this case, because we were actually, really walking, rather than walking around an object and trying to reconstruct the object, you were just walking in a straight line. And then, so the good thing is you can then compute the walking direction, okay? But when you do the reconstruction, the reconstruction is going to be, very bad in a sense that it has lots of holes and lots of problems. But you can see that the direction here was matching pretty well with the sidewalk, actually. So, so one of the bigger problems when you have 360 video is that, where should people look? Okay, in a 360 video, in some cases, yeah, maybe all the 360 degrees are interesting, but in many cases, it's not the case, right? And you want to basically guide the viewer to look at certain things. But then how do you do that? So we did some experiments with basically trying to detect interesting objects and then kind of guiding the user to look at those interesting objects. And one way to do that is to do saliency detection in the frames to try to figure out, okay, which are interesting objects, and then have an algorithm that basically tells the viewer, okay, how about you go from state 1, which is, in this case, what was state 1? Okay, this is on the side here, but state 2 is the Singapore flyer, okay, over here, and then state 3 is the Helix Bridge, and state 4 is the financial center. So you can kind of try to guide the user along the path, okay, so that they actually catch what's interesting in the video. Okay. So this work was done a couple of years ago, but we might pick it up again because of this interest in the metaverses and 3D environments. So this was the second part. Anybody have questions about this part? Because then I'm going to go very quickly to the third part. It's the lens limitation. Yeah, I think it's definitely, 360 cameras come in very large quality variations. You can get some of them for probably now $150 with plastic lenses. And then you can get cameras with, that consist of a dozen or so high quality cameras in a ring orientation with high quality lenses with very high resolution. So it's really, you kind of get what you pay for. And yeah, the low-end cameras, but they have improved a lot recently, I have to say. Many years ago, we did some experiments where we actually had a single camera, and then we had a special spherical mirror on top of that to project 360 degrees into the camera. And then you get, regular HD resolution for over 360 degree, and the quality is really bad. But, that was the early days. And nowadays you can probably buy $10,000 cameras that give you really good results. All right. So let me quickly tell you about a new standard that just recently came out, which is CMCD. And as I mentioned earlier, basically, the whole idea is that in a regular dash system, okay, you have the server, which is basically HTTP server, which is stateless. Okay, so the server doesn't really remember much about the different clients. And so each client requests through usually a cloud and the whole internet backbone, CDNs request pieces of a movie. Okay, and one of the problems that the video providers have is that, so they get requests for these pieces, but it's very difficult for them to aggregate that into even sessions, even to figure out, okay, so which pieces, which requests actually belong to one client and to one session, and how is this client doing? So CMCD is a protocol so that the client can send some information to the server, okay? And the server can then basically get aggregated data and get better insights. So there are currently solutions that do that, so there are special analytics companies but what happens with these analytics companies is that you need a special plugin on the client, and then those plugins, they send information to the analytics cloud, and then that cloud, you subscribe to the cloud, they can give you information. But the industry was interested in something more standard, something that was more interoperable, etc. So now the idea is that basically the clients send, with the requests, they send information to the CDN servers, which then can send that standard information to the analytics cloud, and you can build your own analytics cloud. Okay. And so the fundamental problem is this one here, where you have every client operates separately, every client measures the bandwidth separately, but part of the path may be the same. So then it turns out, some client may switch up to higher quality, some client may switch down to lower quality, it may be unfair. It's just not very, it's not a very fair situation, and sometimes it can be a bit unstable as well. Okay, so you can see here, the clients switch up and down all the time, which is not very good, actually. So so the clients basically compete on the network, and there's all kinds of issues with that. And so the standard tries to address this issue by sending information specific from the client about a certain session to the CDN, and then the CDN can send that to an analytics cloud and inform the server, and the server may be able to actually adjust things a little bit. Normally an HTTP server will not do any bandwidth management or so. They will just send out the pieces as the requests come in. But so we actually tried out a very simple system here, where we have the -GS client, which has this CMCD, supports the CMCD protocol. Okay, then we have the network emulation here in the middle, and we have an Nginx HTTP server, and then we built a plugin here which would basically kind of look at, okay, how are the different clients doing, and maybe I give some hints to the different clients that, okay, you shouldn't switch up to higher quality, maybe to another client. Yes, you can request a high quality piece, give some information. A very simple setup here. Okay, so so basically the requests come in. They come in with this payload of information such as buffer levels and other information, and then the server actually looks at how the different clients are doing, and it's doing some bandwidth allocation basically for the different clients. Okay, and then with the network emulator, we were actually limiting the bandwidth for different clients at different levels, so that they don't have complete freedom how to choose their pieces anymore. Okay, and so this is a very simple protocol, basically a text-based protocol that is the data is sent as part of the requests, and so it's a sort of a key value protocol. So you have a key and then kind of an equal sign here, a key, an equal sign, and a value. So you can send, BMX is the maximum buffer. In this case is 30 seconds. The minimum buffer here is 500 milliseconds, etc. So this is encoded as part of the request, HTTP request. And so the black part here is there's some predefined keys, and then you can define your own keys as well, if you like. And so, we built a very simple, on the server side, we built a very simple scheme, which is basically just looks at the buffer, and it has sort of two thresholds, and it says, okay, if the buffer level is below the minimum here, then we consider this as low buffer. If the buffer level is beyond the maximum, we consider this as a high buffer. And in between, we have this linear linear curve here. Okay. And so the server will then allocate some bandwidth level to the different clients in order to treat them more fairly. So then we wanted to see how well that works. So we had a number of different experiments with different types of clients. Of course, it only works if you have multiple clients, right? So we have 5, 10, 20, and 30 clients. We had different content. BBB is Big Buck Bunny. That's one of the movies that everybody uses for testing. We had some mixed content, and we did some low latency experiments as well. And so, yeah, so we did different combinations, different access links, different capacities, different number of clients, different content, etc. So, yeah, here are some more details of the experimental setup. And then here, these are some of the profiles that we use. So Cascade is, you can see that this is the bandwidth profile here. It's called Cascade because it goes kind of the step function down and then it goes back up. The spike is very nasty. It basically has lots of bandwidth, almost no bandwidth, lots of bandwidth, no bandwidth. So this is a very tough profile. And then the number behind it is the number of clients. And these are the bandwidth values. So it goes from 50 megabits to 20 to 10 to 5 to 10 to 40, etc. And yeah, so then we looked at different metrics. What is the average bit rate that can be achieved, the minimum bit rate, the average number of rebuffers, rebuffering duration, the maximum rebuffering duration, how many times the client rebuffered, how many times it switched, and then the latency as well. And just a few quick results here. So you can see, so when we have basically compared when we have CMCD, when we send the information to the server and when we don't send the information to the server with the cascade with 10 clients. And you can see here basically that, if you have CMCD, we have the number of the rebuffering duration is definitely significantly reduced, okay, and the maximum time is also significantly reduced, okay, and the rebuffering count as well. The average bit rate suffers a little bit as well, but not terribly, right? So the average bit rate goes from 3.33 to 3.13, so it's not terrible. So if you have, this is the spike protocol, again, similarly, we have quite a bit of improvement. We sacrifice a little bit of the average bandwidth. Okay, this is with 30 clients now, and with 30 clients, you can see actually the benefits are much less, okay? There's almost no improvement here if you look at the numbers, okay, with CMCD versus no CMCD. And the reason is basically that the more clients you have, then you sort of statistically things sort of average out over the network, right? So the server can be sort of less beneficial by allocating bandwidth, okay? And then we did some testing to look at the low latency cases, and we can see that actually the latency actually improved slightly from 2.75 seconds to 2.34 seconds with 5 clients. Okay, so actually we were able to get some improvement here as well, and with the spike profile as well, slight improvement. Okay. So this was a very, very simple experiment because CMCD has many, many different parameters that you can send to the server. This just came out recently. People are experimenting with it. The big companies are experimenting with it, trying to figure out what they can do with this information that they get from the client. And then there is a companion standard that recently came out. So one of them is the client sends information to the server, and then there's something called CMCD, where the server sends information to the client. Okay, and again, there's all kinds of information you can send, and some of the research questions are: what can you do with this information? How can you improve these very large-scale systems? Okay. So basically the takeaway here is that information exchange is useful in these very large streaming systems. There's code available, open source code. There's lots of questions, what information is relevant, what is actionable, what should we be using, what should the CDNs be using, etc. And it's all pretty much open source. Anybody can contribute in this WAVE project. Which is, so it's kind of coordinated on the WAVE. Okay. And so these are the different contributors, and our code is available as well. Okay, so that's pretty much it. Sorry, I was running late here, but I think we still have some time for questions. And so Roland was asking here, can we think of this as a kind of real-time distributed optimization problem? Yeah, definitely, yes. And it's a very large-scale optimization problem and very real-time, right? I mean, if you look at YouTube, how many streams they have running, and also that the distributed system is quite complex, because you have the origin servers, and then you have the CDNs, which have hundreds or thousands of CDN caching nodes, and then you have the clients that are connected to these caching CDN nodes. And for the operators, it's really important to know what's going on, what is the quality that the end users, that the end users experience, because, people complain if the streaming doesn't work well, right? But how do you know if you're Amazon? How do you know if, Roger in Singapore has a good experience with their stream or not? From a business point of view and from a technical point of view, it's very challenging to know what every client is doing, which clients are suffering. And then, you may dynamically want to switch some clients to other CDN nodes. You might need to switch whole areas of the network to another CDN. All of this should happen sort of in real time to give people the best possible experience, and for them to not notice that there's all the stuff that's going on behind the scenes. Yeah. So definitely the model becomes very complex. Even just having the insights of knowing what's going on, even before we try to automatically fix things, right? Even just having a dashboard that tells me, okay, Singapore is doing well, Malaysia is not doing good, not doing well. Even just that is very important for the operators. All right, so thank you everybody very much. And yes, please, if you have any additional questions, I'll be happy to answer.
I think, I just wanted to ask one question. In the second part of the talk, you mentioned about interesting scenes. So there also seems to be a question about what do you call as interesting in a scene. So you mentioned that the Singapore Bridge, and so how do you define interesting in this context?
That is a very good question, actually. And I think it's actually one of the reasons why 360-degree videos haven't really taken off that much. Because if you look at traditional movies, for example, it's usually the director that wants to convey certain things, right? The director wants you to look at a certain area or a certain scene or get a certain emotion across. And by having a relatively narrow view, that's possible. But if you have 360 degrees, then the viewer could just look at the completely wrong piece, not where the director wants you to look. So that's actually, I think, one of the reasons why many directors don't necessarily want to make 360-degree movies, because they lose a lot of control. So yeah, I don't have a good answer for this. I mean, if you put a camera underwater and there's lots of interesting fish, etc., so then I guess it doesn't matter too much. You can just look around and it's fascinating. But in other cases, you may want to direct the viewer attention somewhere. And then how do you do that? And what is interesting? I mean, yeah.
By directing you, sorry.
Yeah.
One way is to
crowdsource it, right? You could tell, it just measure where is everybody looking, and then that's the interesting part. Sorry, yeah.
Yeah. No, yeah, I just wanted to complete that by directing the attention, we are again going away from the 360 degree, because now you are again saying that just focus on one aspect of the scene. So, or maybe the other way to ask, are there situations where one really wants to look all around? I mean, like, do we need the 360 to?
Yeah, that's a good question also. Because I think that maybe, I mean, there's a certain novelty aspect to 360 video, and I guess if you have a camera in outer space, it may be interesting to look all around, or underwater, it may be interesting to look around. But then there are definitely other situations where a certain direction is more interesting than others. But yeah, I think this is one of the areas where the sort of the artistic tools and artistic rules haven't really caught up with the technology. How would the directors actually utilize this? Yeah, I think this is a very important open question. Yeah.
There's another question on the chat.
Yeah, how is low latency achieved in the case of two-way video conferencing? So most of the two-way systems use something called WebRTC, or basically the RTP protocol, which is a packet-based protocol, which is, it doesn't use HTTP. It's often based on the UDP protocol. Then it has the issue with firewalls. A lot of companies block UDP ports. You have all kinds of issues, but you get the shortest possible latency. So the browsers include WebRTC libraries. So with some simple JavaScript code, you can actually build your own video conferencing system, at least for 2-3 people. But many times you might need some kind of a central relay node to send the traffic through, because connecting two nodes behind NATs is non-trivial in many cases. So yeah, so that was actually, I think, Skype. When Skype first came out, that was one of their achievements, that they made it look seamless. So they did all this kind of, NAT hole punching. They switched between UDP, TCP, and even in some cases HTTP protocols with all kinds of tricks in the toolbox. And they made it so that you installed Skype and it just worked. And that really, I think that was one of the reasons why it took off. but they put a lot of code and a lot of clever programming into making it work with low latency. And nowadays, I guess it's a little bit easier because you can have these, you can have a cloud network of relay servers, and then you can get fairly low latency, and you can get around some of these issues with firewalls, etc. But yeah, Zoom, these large-scale video conferencing systems, that's some heavy real-time programming there. Yeah, real-time networking programming that they do. Yeah, it's nice. It's definitely not as simple as it sounds. Yes.
Okay, so I think we are coming close to our allotted time here. If there are more questions, Roger is back to Singapore, so he'll be
send me email
around. Okay, so with that, I would like to close the session for this week. We'll be meeting back in the first week of February. There will be an exciting talk by Ilya Sergey. So until then, thanks everyone. Thanks again, Roger, for a very interesting talk. And thank you.
Thanks everyone, and thank you for having me.